Photolithography, used for nanotechnology, has many steps and requires a few basic materials. Photolithography starts off with a substrate, also known as a base, which is usually made of very pure silicone. Right now, we're looking at a silicone wafer from a bird's eye view. This thin silicone wafer is used to print multiple small chips. The silicone is cleaned to remove any particulate matter on the surface, as well as any traces of organic, inorganic, ionic, and metallic impurities. After the substrate is cleaned, a desired material is added onto it. Usually this takes the form of some sort of metal or conductor. Photoresist is then applied evenly over the first layer. Photoresist, also known as resist, is the secret sauce in photolithography. It is a substance that, when exposed to light, becomes soluble. This means that any part of the photoresist that is exposed to light can be dissolved in a liquid. This is the main component in making the nano patterns. There are two main types of photoresist: positive photoresist, which is the example you just saw, where the resist exposed to light becomes more soluble, and negative photoresist, where the resist exposed to light becomes less soluble than the resist that wasn't. This layer is then soft baked, which is a process where the whole object is quickly baked or microwaved to optimize the light absorbance characteristics of the photoresist. A mask, which is a thin flat object with cutout patterns, is held in between a light and the photoresist. This mask is traditionally made up of two layers: chrome, a material that blocks the light, represented in black, and glass, a material that allows light to pass through, represented in white. The pattern on the mask is transferred to the photoresist through the exposure process. The exposure process is where a mask is held in between our object and a light source. The mask can be positioned in three ways. The first way is through contact. The photoresist is exposed to the light while in contact with the mask. Because of the contact between the resist and the mask, very high resolution is possible in contact printing. The problem with this kind of printing is that debris trapped between the resist and the mask can damage the mask and cause defects in the pattern. The second problem is that the pattern can be printed only as small as the mask is. The second type of printing is known as the proximity exposure method, and it's similar to contact printing, except that there's a small gap, usually 10 to 25 microns wide, that is maintained between the wafer and the mask during light exposure. This gap minimizes but may not eliminate mask damage. The final way to position the mask is by using the projection printing method. Light that is passed through the mask shines through a reduction optic lens that shrinks the light pattern onto the photoresist. Developer is then used to wash away the soluble photoresist. The object is now etched using a chemical agent that removes the first layer that isn't covered by photoresist. A liquid resist stripper chemically alters the resist so it no longer adheres to the first layer, leaving a pattern of only the first layer. Silicon dioxide is added onto the substrate, filling in the areas where the first layer is absent. This process is then repeated to create as many different patterns as necessary until the final goal is achieved. Remember, Today's chips have up to 30 layers of circuitry. The wavelength of the light source used in this process is actually not in the visible field. The visible field ranges from 400 to 700 nanometers. The wavelength of the light used in photolithography are considered deep ultraviolet, with a wavelength of 193 nanometers. Argon fluoride lasers are typically used to create this light that is so important in the process. As shown, photolithography can serve as an effective technique to printing single layers or multiple layers of nanopatterns and integrated circuits. But what about printing more complex 3D objects, like nanobots? Well, in this case, another printing method may be faster. This method is called two-photon polymerization, and it's great for printing complex 3D objects with resolution down to 100 nanometers. The two-photon polymerization technique is based on the interaction of femtosecond laser radiation, which induces a highly localized chemical reaction leading to the polymerization of the photosensitive material. That's a lot to take in, so let's compare it to photolithography, something we've already looked at, and see how it matches up. Compared to photolithography, two-photon polymerization is a simple process for creating nano objects. Two-photon polymerization uses light to cause a chemical reaction in certain materials. These materials are usually referred to as polymeric resin or polymeric materials. Unlike photolithography, however, these chemically activated materials end up being the final product, instead of just a step in the process. Polymeric material is typically a photoactive or light-active resin made up of monomers. Monomers are molecules that can be bonded to other identical molecules to form a chain of monomers, known as a polymer. So basically, when polymeric material is exposed to an appropriate light, it begins to polymerize. This is to say that the monomers begin to bond to each other, where the appropriate light is present, and begin to form into a polymer. Two-photon polymerization starts off with a femtosecond laser that generates light with a wavelength of approximately 800 nanometers. This femtosecond laser pulses every few hundred femtoseconds, a femtosecond being 1/4,000,000th of a second. This laser is bounced off a mirror and into a galvanometric mirror scanner, or a GMS. This GMS is used to control the direction that the light takes. The light that is aimed by this GMS is precisely funneled into an objective lens that takes the straight laser beam and points it inwards so that its vertex is in the polymeric material. The material polymerizes only at the vertex, where the light is most acute. The platform that the polymeric material sits on moves up and down to allow for complete 3D control by the printer. There are many possible polymeric materials that can be used in two-photon polymerization. Different materials work best for different applications. Peter Petrochenko, a biomedical engineer for the FDA, has begun testing an elastomeric porous polymeric material to build scaffolds for supporting human bone stem cells. Due to the porous nature of the material, cells are able to grow into the scaffold every which way, and due to its elastic quality, the scaffold is able to withhold significant pressure without breaking, which would be really helpful when putting it in the bone of a patient. Two-photon polymerization has many possible applications, medicine being one of the biggest fields that it can apply to. Some future applications include scaffolds for internal and external body repair, drug administration nanobots that deliver a patient the proper quantity of drugs to the right place at the right time, and nanobots that can determine if an organ is unhealthy or developing illness. But how can we get these technologies to become small enough and smart enough to take on such roles? Nanoscientists' answers and propositions vary tremendously, but it seems like all future predictions of nanotechnology fabrication fall into two categories: a top-down approach and a bottom-up approach. The top-down fabrication approach means that nanomaterials are created by direct manipulation of a material. This is to say that in the top-down fabrication, a person or machine must in some form etch away at a material like we see in photolithography, or build into a material like we see in two-photon polymerization. A bottom-up approach is where nanotech builds itself from individual atoms that are piled up one at a time to build a structure. You can think of a top-down approach as a sculptor that has to turn a slab of marble into a beautiful sculpture, chipping away at the marble until the sculpture is complete. You can think about the bottom-up approach as a pile of sand that has to self-assemble into a beautiful sculpture, like this beautiful sculpture of a ghost thing. The latter approach is usually the one glorified in movies, like in the clips we saw from both Endgame and Black Panther. This bottom-up approach has been perfected by Mother Nature over a period of several millennia, but nanoscientists are hoping that it won't take us that long. Here are some popular bottom-up techniques if you're interested: Solgen synthesis, vapor deposition, atomic layer deposition, molecular self-assembly, and finally DNA-assisted assembly. In conclusion, nanotechnology is an amazing innovation that has, in only decades, brought the far future of technology into the present, giving all of us today 1970 superpowers. Thanks for watching.